All right, good morning or good afternoon or good evening, wherever you are. My name is Inmar Givoni. I'm the Director of Engineering at Uber ATG R&D Lab, and today I'm going to tell you about deep learning for self-driving at Uber ATG and all of the stuff that we've been working on recently. So just a little bit about our office. We started just over 3 years ago as a group of 7 researchers from the University of Toronto, headed by Professor Raquel Urtasun. He's also one of the co-founders of the Vector Institute and the chief scientist and head of the office. There are over 60 people right now in our offices. And just a little bit about myself. So I have a background in machine learning from the University of Toronto, where I did my PhD. And after my graduation, I wanted to work in industry. My passion has often been about taking cutting edge AI research and really bringing it into production systems. So I've worked on systems from the Kinect gaming system to robotic systems for warehouse fulfillment. And just about 3 years ago, I joined the Uber ATG R&D office that had just opened in Toronto to build the research engineering team there, where most of my focus is about bringing some of these cutting edge algorithms that are developed by the research side into the production systems. So let's talk a little bit about why we want to do self-driving. So obviously, it's an important thing to try and solve. Back in the days, we used to train our horses to take us back home when we went maybe to the bar and had a few more glasses. And nowadays, we can train our cars to do the same thing. It's also important because over 1.3 million people die annually from car-related accidents, and most of them are because of human errors. With self-driving, we can provide mobility to people who cannot drive by themselves. With self-driving, we can reclaim a lot of the public spaces because we won't need as much parking spaces for cars. We can just have services that pick us up and drop us off wherever we need them, and so on. Self-driving is also incredibly complicated. So in this video, I'm showing you in purple the self-driving car. This is based on some information from logs we have collected. The circular dots are pedestrians. Other black squares are other cars. And what you will see is that there is a lot of stuff that the self-driving vehicle needs to understand. It needs to understand where everyone in the scene is, where they might be going, what are the rules of the traffic, so which lane can go into which other lane. There's a lot of unpredictability because you need to be prepared at any given moment for a pedestrian, say, to do something unexpected, like a child running into the road and chasing after a ball, and so on. So with all of that in mind, we need to solve a very complicated problem that also has a lot of what we like to call, the long tail. So a lot of different edge cases that you don't see often, but when you do see them, you need to be prepared for them. For example, construction sites where the actual layout of the road and where you're supposed to be driving or not supposed to be driving changes overnight, and you need to be able to parse the information in real time. So how do you actually go about self-driving? Well, first of all, you need to understand your surrounding. This is our current model of the self-driving vehicle. The most prominent sensor that allows us to sense the environment is this large conical shape at the top. That's the LiDAR. So it gives us a 360 degrees 3D scan of the environment, or in other words, it tells us how far away things are from the self-driving vehicle. This is the most important aspect of the LiDAR. Then we have an array of cameras just below that are giving us a view of the environment with more standard imagery. There are radar sensors, there are internal measurement units, there is a very large set of compute at the back of the car that allows us to run all of these computations in real time. So we're talking about CPUs, GPUs, a big cooling system to allow for all of that to not overheat the car, and so on. So it's a very sophisticated piece of technology with multiple hardware, software, sensor components. But ultimately, the question of self-driving is that of going from sensors to controls. So what I'm showing here on the left is one of the cameras, the front-facing camera, and the view that we get from driving around. And then here, this purple-blue visualization is what you get from the LiDAR. The LiDAR is three-dimensional, so of course, if we want to show it, we need to decide how we're going to display it as a two-dimensional thing. Here, what we're doing is we're taking the top-down view. So we're looking as if we're looking at the three-dimensional scene from just above the self-driving vehicle, and we're squishing all the information just so that we can render it as a two-dimensional image. And so what you end up is something black in the middle, which is actually the self-driving car. And it's black because, of course, it's occluding itself. It doesn't know anything about itself. And then the layout of all of the street information around it. And even though when you look at it for the first time, it might seem quite incomprehensible, over time you will kind of like, a doctor on x-rays, you will start noticing a lot of the details. So you'll see the buildings, you'll see some pedestrians, other cars, and so on. So these are the two types of information that we have if, let's say, we're focusing on these two particular sensors, and we need to go from this sensor information to controlling the car, which is basically the steering instructions, so right and left, and the acceleration and deceleration. So that's the fundamental problem of self-driving. Now, since I've said we go from sensors to controls, how do we go about solving it? So the traditional approach of what we call the autonomy stack, autonomy, the name given to this task of going from input to driving output, is to break it into a whole bunch of sub-problems and treat each one of them individually and solve it individually. And then let me just take you through these types of problems. So our input is the maps and the sensors, and our output is the control, which we said is steering and acceleration, deceleration. So the first thing that we want to do, so here I'm showing the sensor information. Importantly, we also have access while we're driving to very high definition maps. These are not like your Google Maps. They show a lot of details. So here you can see a rendering of the map information. So you see each and every lane. You have some information about the type of separator that you have between the lanes. You see which lane can go to any, what are the rules for each lane to go into any other lane, and so on. So these maps are extremely detailed. They also tell you where all the traffic lights are going to be, and so on and so forth. So, and it might be surprising to know that, but most self-driving solutions nowadays are based on having this pre-recorded and pre-sorted information about the map, as opposed to trying to decipher it all on the fly. Once we have the maps and the sensors, the first typical traditional task is that of perception. So the perception task is basically, I want to detect everyone in the scene that is going to be moving around potentially and doing things that are unexpected, that are not on the map itself, that are not static. So in this case, this would be vehicles, motorcycles, bicycles, pedestrians, and here I'm showing you with these different squares, all of the detections that a system might need to do based on this particular input. It's not enough to just detect. You also need to track where individual objects are going, because these systems typically do a detection task over every frame of the LiDAR. So the LiDAR rotates at about 10 Hertz, so 10 times a second. You have information about the environment, and each time you can do the detection task and see where the dynamic objects are, or the objects of interest are. And you want to do it over time. You want to know that the detection of this car in this frame is the same as the car from the previous frame. And the reason you want to align these two detections is because then you can start thinking about things like, how fast is this car going? And you want to think about estimating these types of measurements. So you want to be able to also track across different frames the objects that you've detected. So that's typically the perception task. Once you know where everything is and maybe how fast they're moving, so you're tracking them, the next thing you want to do is prediction. Prediction is basically saying where do I think this particular object is going to be over some time horizon. So perhaps, for the next, let's say, 10 seconds or so. And here I'm showing a hypothetical prediction of the system. Well, it's not hypothetical, it's actually based on a true system, but from the point of view of the visualization, you can see that there is a little line, or it's really a set of dots emanating from each one of the detections. And that's basically where we think the car is going to be in the next 100 milliseconds, 200 milliseconds, and so on, for about a total of 3 seconds, I believe. Okay, so now we know where people and objects like cars are, and how fast they're going and what is the direction they're heading in. And we also have a prediction about where we think they are going to be in the next few seconds. So now we're ready for the next task in this pipeline system, which is planning. So planning basically says the self-driving vehicle, because of where it's heading, needs to, for example, for this next little section of the road, it needs to just stay in the same path, in the same lane, and follow, of course, the traffic rules. Now, in order to do that, at the very least, it shouldn't bump into the car in front of it. So based on knowing where the car is and where we think it's going to go and how fast, we can plan the trajectory of the actual self-driving vehicle. And by trajectory here, I mean, where should it be in the next time horizon? How fast should it go? And so on. So that's the planning task. And now we can actually take this information and send it to the control system to basically execute this maneuver. So this is how people have traditionally looked at how do we go from this sensor information to the control system. And here, what we're seeing is basically how it all looks like when we put it together and display it in video. So just for visualization purposes. So at every given moment, we know where all the actors are, we know where we think they're gonna head, and we plan our execution. Now, there are issues with this traditional approach. There are some benefits to it. So it's very interpretable. We know why we're doing things. We know what we think the car perceives at any step of the way and its predictions and so on. So we have what we call this intermediate representation, and they're very important for in determining the safety of the system. And it's very easy to incorporate prior knowledge. So we can easily inject things like the rules of the traffic into the algorithm. The issues with this approach is that the reaction time, because you have this pipeline system, can become longer and longer as you add up more and more computation. It's very difficult to develop effectively, because if you are someone working on the planning side of things, you really depend on the output of the perception and the prediction systems. And if they have issues with their outputs, you're kind of stuck, and you might need to start injecting temporary solution and so on. And over time, it just becomes a very difficult pipeline to maintain and to improve. And finally, you're not really training your modules for the end task. And what I mean by that is your perception system, if you think about it from the point of view of the objective function, it's not really trying to solve for self-driving. It's just trying to solve for detections. And so it's very hard to incorporate into it what is common sense information, which is the car in front of you or the car moving towards you at an alarming speed is much more important to detect and track than cars that have passed you and are moving in the other direction. But there's no way of explicitly telling the algorithm to do that without trying to manually set up all of these different rules. Where we really want the signal to come from is the actual driving experience, so from the end of this pipeline. The alternative approach is to basically take a large neural network to give it as input the sensor, to give it as output examples of people driving, and to tell it to learn how to drive. So that's the end-to-end approach. It's very simple. It's a single AI system, and you are training it for the correct task. The problem is when it goes wrong, you have no idea what happened and why it went wrong. So there is no interpretability, and therefore you can not have a lot of guarantees on safety and validation. And also there is no easy way to incorporate prior knowledge like the rules of traffic. You've just given it the maps and sensors and demanded a particular output. So one of the big things that we're trying to do at ATG is this idea of a trainable end-to-end system that is also interpretable. So we basically want the best of both worlds. We want one big neural network that does understand these intermediate steps and emits intermediate results. And what we get from that is we do benefit from lower reaction time because we do have a lot of shared computation. For example, all of the features are computed through one area in the backbone of the network. We can incorporate prior knowledge because it's a structured network. We can inject information. It is end-to-end trainable and so easier to work on. And it's solving for the task at hand. And importantly, as I said, it has this interpretable intermediate representation, which are very important for safety. And this is what we think of as the interpretable neural motion planning and so that's where we're heading. First, I'll show you a system that is not doing the whole stack, but it's the first perception and prediction joint system, and it's the first of its kind, and it's implemented on our system. So we're taking the two first parts of this pipeline and putting them into a single network. And here is a visualization of the system. So the system is basically both detecting all of the different vehicles in the scene, as well as predicting where they're going to be over the next time horizon, which you can see by these very colorful displays. And if you're paying attention, you'd also notice that it's able to do things like multimodal prediction. So the prediction of any car location doesn't have to be a single lane. It knows that sometimes, let's say around intersection, a car might choose to either continue going in the same direction or maybe split and turn right. The next thing we did was start actually working on interpretable neural motion planners. Here I'm showing you a succession of 3 publications from last year and from this year that are showing more and more advanced types of neural network that basically go from sensors to control. And this is showcasing how we're kind of making strides towards our end goal. And this is a visualization of one of them. So as you can see, this is a network that does perception, prediction, and planning jointly. And this is the way we're visualizing it is basically by these colorful displays that are visualization of where is a good place for the car to be. And so this is the self-driving car here. And it's estimating for all the other cars, where are reasonable places for them to be? And based on that, it's doing its planning. Moving on to other things, a lot of people are curious about vehicle-to-vehicle technology. When are we going to be able to use the fact that these cars can communicate in order to do better driving? And indeed, we've been working on that problem. On the left here, you can see if this self-driving car, the one that's moving right, is not able to see the child that is about to run into the road because they're kicking a ball, but the car over here is able to see that and hopefully can transmit some information to the other car. So the real question here is, the idea is very straightforward. The question is, what is the information we want to transmit? Because we can transmit the entire sensor array that this car is seeing, but that's a lot of information, and you also need to figure out how to mesh up the two representations, the one coming from the self-driving vehicle and the one coming from its neighbor. Whereas if you only send it things like the detections, it's not a lot of information to send, which is good. You're not spending, wasting a lot of your bandwidth, but it might just not be enough. And so what we are exploring is how to send this intermediate representation that again capture the best of both worlds in terms of enough richness, but low bandwidth requirement that is the most helpful for the self-driving car. And indeed, we're seeing 70% decrease error in perception, for example, when we're simulating this technology. And here what you're seeing on the right is 4 different self-driving vehicles in simulation and the different visualization of what they're seeing based on all the information they're also getting from the other cars. And so in the previous example, I've shown you a system that was mostly tested in simulation, which takes me to the next thing that I wanted to talk about. So simulation is incredibly important for self-driving vehicles because we can't test everything on the road. Obviously, there are a lot of very unlikely and dangerous cases that we want to make sure the vehicle is prepared for, but we don't have the opportunity to test them on the road most days, luckily. But we really do need to make sure that we test them. Also, it gives us the opportunity to run different scenarios at a very, very large scale that manual testing on a track or on the road is not going to allow us. The problem with simulation is that if you really want to test your entire system, you need to properly do things like simulate the sensors. And simulating sensors is quite hard. It is not that hard to simulate what looks to a human like a reasonable image or a LiDAR image, but actually from the properties, the actual physical properties of the simulation that are attempting to replicate what the sensors are getting, including all the noise and all the errors and so on, that is quite a different task. So we've been working a lot on sensor simulation technology. Here what you're seeing is information that we gather on the left from logs, sometimes even by incorporating many, many logs. So this is actually LiDAR information. The reason it looks so rich is because you're collecting a lot of points over time. And so you're getting something that is actually quite rich in detail, even though it's LiDAR. And with that information, we can learn how to simulate the LiDAR sensor information that the car, that is close enough to what the sensors on the cars are picking up. And here we're seeing some results of running a detection algorithm. So the detections are the red squares based on simulated LiDAR. So we've basically built a 3D reconstruction of the scene, and then we say if we were to send the laser information and read it as it bounces back, the way the LiDAR works, what are we going to see if we train a neural network to properly distort the signal based on what we see also in reality. And of course, we can do that at an incredible scale and run hundreds of thousands of different simulations, and that really helps us improve our systems. The next thing that we want to learn how to simulate, of course, is cameras as well. It's very difficult to simulate the full scenarios with all the houses and the trees and so on. And really, there is no need to, because what we really care about is simulating the actor. So what you're seeing here is how we are learning to take some sort of an object. Let me play this one again, like a car, and render it within the scene. So in order to do that, you need to account for things like changes in lighting conditions. You also need to account for when the car is making a maneuver where it's turning or so on. You need to be able to properly modify the information that you have about this asset. So this car basically was captured from different angles in a different log, in a different log completely, and we're computing, in-painting, and transforming the visualization of the car so that it actually fits the geometry of the scene. And so this allows us to properly simulate camera. A word about how do you take this exciting technology and put it onto the car. So this is where me and my team often spend most of our time. It has a lot of different aspects and complexity, anything from the data wrangling, so being able to bring all of this complex sensor data and map data and labeling data to the algorithm so that they can be properly trained. Once we have a neural network that is properly trained and we see good performance results, we also need to care greatly about the runtime and performance optimization of the models. So we spend a lot of time working on things like taking particular pieces of code and making them run on GPUs, making them run with lower precision, making them run with a network that has a slightly different architecture than the original, but is faster or while not compromising on the performance and so on. So we spend a lot of time there. How do you train within a production system that's live and needs to be a very stable environment? It's not a side project that's detached from it. How do you integrate the inference into the full system, which is, it's a full robotic framework where you have messages floating around and everything needs to come to the right place at the right time. How do you deal with the system level testing and metrics so that you're able to confirm that, yes, this neural network does really well in terms of the objective function it's been trained on, but really what we care about at the end of the day is the full system testing and the full system performance. And how do you deal with the incredible demands on compute and storage for running these very large scale deep learning type of systems? And so with that, I'll close. Thank you for attending the talk, and hopefully I'll be there for the Q&A.
Thank you, Inmar. Let's see what questions have come in. Oh, first a comment. Okay, here's a good one. I love to listen to talks like this, discussing her successful experience in solving a tough problem. It's not theory or speculation. So thank you.
Yeah, thanks for the comment. Else, I see my video feed very, very choppy, so apologies for that. Okay.
All right, we're having a little bit of technical difficulty, so give me half a second. I've got to switch over and jump out and jump back in. So Inmar, while I do this, there's a question about LiDAR sensors and why they would be used and not. Maybe you could address that one for a moment.
Yes, so one question from the chat was, why is Tesla reluctant to use LiDAR? While they're probably the best people to answer it, my understanding is because they're selling the cars to individuals. They need to keep the price point at a reasonable consumer product, whereas for the ride-sharing type operation, the considerations are quite different. A safer option because you measure directly how far things are, whereas with cameras, you basically cannot measure distance. You need to compute it. It's an algorithm. It's prone to making errors. So from a safety perspective, most trusted technology nowadays.
Awesome. Okay, here's a good question. This one interests me, so I'm going to pick this one. What if the road structures change? Do you have dense maps based on what it is today?
Yeah, there is the strategy of using maps that I discussed, meaning that we have to go and capture the structure of the road, and we kind of assume that this is what it's going to be when the self-driving vehicle is out there. But of course, you have things like construction, changes in the road all the time. So there has to be a mechanism that detect the fact that the map is out of date, that what the car sees and what it's expecting to see are different, and then kick into a mode where it is figuring out what's going on right now. The reason to use maps is just so that you can save up on some of these computations, but there is obviously a mechanism in place that will allow you, at the very least, a very graceful, you say, I am not able to deal with the current situation, I'm going to come to a safe stop. Or alternatively, if possible, just dealing with the situation at hand and doing what it takes to get back to an area that's properly mapped.
Awesome. Okay, there are a lot of questions rolling in, but unfortunately, we are at time. Inmar, if you've got a couple minutes, I'm absolutely not linked this to you, but maybe answer some of the questions. There's some good ones in there.
Yeah, I can take a few more minutes.
Awesome. So thank you for being here. Thank you for your talk. Obviously, that is very exciting to a lot of us and very interesting. And thank you to everybody for tuning in.